question today for you, Sam.
Fantastic.
True or false? All radioactivity is man-made.
Yeah, so false. Most radioactivity, in fact, I'm going to go ahead and say all radioactivity is not man-made. Human beings can have an impact on how radioactive a substance is, maybe in an effort to do something like develop, let's say, purified uranium for a nuclear power plant, or to develop some type of a core for a nuclear explosive. But let's just talk a little bit about what radioactivity is, and then we'll sort of see why I say that really radioactivity is not something that humans create. So if we could jump to my screen really quickly. Broadly speaking, there are three types of radiation or radioactivity that we talk about. There's alpha radiation, beta radiation, and gamma radiation. Now that's not all types of radiation. What I have in this image right here, as you can see, this over here, this ball of blue and red balls, kind of this collection of them stuck together, that's meant to represent the nucleus of a uranium atom. So one of the things that we learn about in chemistry or physics is the idea that all substances in the universe are made of atoms, and atoms themselves are composed of electrons, neutrons, and protons. And we learn that electrons orbit the outer regions of the atom, the space that the atom takes up, and that the very core of the atom is the part that's made up of protons and neutrons. I'm just going to show really quickly the periodic table. This is a website called ptable.com. It's a really awesome interactive periodic table website. You can check out all the different known elements that exist. All these different elements. You can have an atom of any of these kinds of different elements. So, for example, you could have an atom of hydrogen, where I've got my cursor right now, or you could have an atom of gallium, where I've got my cursor now. And I just wanted to show this to make the point that the periodic table is set up in such a way that it goes from the smallest elements to the greatest elements, reading from the top left to the bottom right. So I start here at hydrogen. Hydrogen is the smallest and lightest element, and then as we move through over to helium next, helium is the next biggest element. And the numbers that you see here on the top left of the element symbol, that's what's called the atomic number. And that lets us know how many protons this atom, or this element, an atom of this element would have. So a hydrogen atom will always have 1 proton, a helium atom will always have 2 protons, an indium atom will always have 49 protons. That atomic number always tells us the number of protons. So I say all this just to make the point that as we go up, or as we go through the periodic table, we get to these really large atoms. Things like, oh God, here we've got gold gets really big, 79 protons. And then probably the most common radioactive element that we think of is uranium. So uranium has 92 protons in its nucleus. And so let me just jump back to this picture really quick. Really large atoms that have gigantic nuclei, nuclei that are filled with tons of protons, but also lots of neutrons. They tend to be unstable. Something that I think is not addressed enough in chemistry and physics classes is the idea that we talk about the idea that protons have a positive charge. But then we sort of just gloss over the fact that you could have an area in an atom like a nucleus where 2 protons, 2 positively charged particles, sit right next to each other, even though we learned that 2 positive charges or 2 like charges should repel each other. Something that we don't often get into is the idea that there are some special forces that take effect on the very, 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 very small scale of the atomic nucleus. So there are 2 forces, the strong force and the weak force, and they only act on very, very, very tiny spaces. So for example, the width of the nucleus. So the strong force and the weak force are these forces that hold the nuclei of different atoms together. However, there's a limit to these forces, and there's a limit to how much they can hold. And with larger elements, typically, we get sort of an unstable nucleus, a nucleus that's not quite held together well. And so particles of the nucleus can be jettisoned off. And that's what we call radiation. Radiation is I mean, and it comes from the word to radiate, right? Like to let something off. So the idea is that the nucleus is letting off different types of particles. Your nucleus might let off the least damaging type of radiation would be an alpha particle. Alpha particles are identical to helium nuclei, so it looks just like a helium nucleus. They have 2 protons, 2 neutrons. Alpha particles are large. And an alpha particle could be stopped by a sheet of paper. Like if somebody was shooting alpha particles at me, I can just hold up this piece of paper and block those alpha particles with it. Beta particles can be stopped by a slightly thicker, beta particles, are electrons that are jettisoned off. You can see here, it's represented by this black dot here. typically what happens in beta radiation is a neutron is jettisoned off and it breaks down to a proton and an electron, the electron being shot off. Beta radiation is also not particularly damaging. It's slightly more damaging than alpha radiation. The kind of radiation you really want to look out for is gamma radiation, which is a highly charged photon. It's essentially just an energy particle that's released from the center of the nucleus, or from the nucleus itself. Gamma radiation, it takes several inches of lead to block gamma radiation. So if you've ever been to maybe the dentist before and had them they might do an x-ray of you where they're shooting what are close to gamma rays at you to kind of get an x-ray of, let's say, your jaw. If you go into the dentist, I've experienced, they'll often put an apron over you that's sort of a thick lead apron or lead-filled apron or some kind of an apron that's filled with something that's meant to block damaging radioactive particles. So again, radioactivity is just this idea of it's an unstable nucleus of some kind of an atom jettisoning off pieces of itself. And we name those different pieces. You can see here that neutrons are jettisoned off, protons are jettisoned off. There are different situations where different things might be sent off. I just also wanted to make the point that it's not only large molecules that do that, or large atoms, excuse me, that do this. We can have, typically smaller atoms are more stable. So carbon's a great example of a pretty stable element. But carbon, normal carbon is what we call carbon-12. So you can see that right here on the left side of this image I've just shown, and let me blow this up a little bit. Carbon-12, it's called carbon-12 because it has an atomic weight of 12. We calculate that atomic weight because it has 6 protons, 6 neutrons. Each proton or neutron has an atomic mass unit of 1, or mass value of 1. So we add those together and we get a total weight of 12 atomic mass units. That's a typical carbon atom, and the vast majority of carbon that exists in the universe is in the form of carbon-12. But in certain situations in the formation of carbon, elements are typically formed inside of stars. It's typically the heat and pressure inside of a star, like our sun, that allows complex elements to be cooked, like carbon. You can have situations where special kinds of carbon are created. Now, all carbon has to have 6 protons. The number of protons in an atom always dictates what kind of atom that is. So carbon has got to have 6 protons, but carbon could have more than 6 neutrons. In this example, we see carbon-13 and carbon-14, carbon-13 having 7 neutrons and carbon-14 having 8 neutrons. Carbon-13 and carbon-14 are less stable examples of carbon, and so in fact we do get radioactivity from these forms of carbon, from carbon-14, for example, and we do actually radioactive dating using carbon-14. Something I haven't totally gotten into is this idea that radioactivity actually happens at a really consistent rate. Radioactivity, atoms break down. They have what's called a radioactive half-life, and the timing of the radioactivity, the timing that it takes for carbon-14 to break down to carbon-12 is a consistent time. It's a time that we can count on. And I don't know specifically what that is, but we would use that time and we could look at, let's say, we could figure out generally how many carbon-13s we would expect to have in a sample, how many carbon-12s we would expect to have in a sample, and then looking at the sample itself and seeing how much carbon-13 and 12 we could make a guess at, or a good estimate at how much of the carbon-13 had converted to carbon-12. And that would give us a sense of the time that it took for that to happen, which would be one way that we could date that object. I went over that really fast. That's not a great explanation of it, but I just thought I'd add that in there. Generally speaking, radioactivity is just this property of unstable nuclei of atoms. It's not something that people create at all, but of course human beings have figured out ways to manipulate it.
Okay, really interesting.
Yeah, interesting stuff.